Okay. Good afternoon. My name is Michał Burdukiewicz, and it is my very pleasure to start this whyr webinar. I'm very happy to see that we have already so many R people in our chat. Please write where are you from. We will be very happy to one day host your webinar. But this evening, I have a pleasure of introducing a very not maybe unique, will be a bad, won't sound that good, but a very special guest. So Bernd Bischl. I don't want to talk about his academic achievements. Professor of LMU, it's a lot of quite a bit of grants and great publications. I want to present him as a member of our community, and moreover, a man with a passion, man with a dream of creating a wrapper for machine learning in R. And this dream started quite a bit of quite a time ago when we had what we had. I think only was a very preliminary version of Caret, or even a little bit before. So that's what Bernd did, and this amazing effort, MLr package, and the whole ecosystem is continuing over years, and it produced many great additional packages like tools for Bayesian optimization, batch tools, a very unique and a very novel idea of implementing batch computations in R, and also other tools related to the machine learning. But of course, Bernd, as every project like MLr grows, and Bernd being an academic, he already is growing up his students. So today this webinar is co-hosted by two of his PhD students, Florian and Martin. Both are in Bernd's group in Munich. Both are heavily working on machine learning applications. Martin has a bit more of biological task, which myself as a bioinformatician, I like it. But Florian has a slightly more theoretical edge, but both of them will be here for us during the rest of the evening, ready to answer questions about the MLr and specifically MLr3 and MLr pipelines. So without any further ado, let's clap behind our computer screens for Bernd. And Bernd, the floor is yours. Go on.
So I guess you can see my screen share now, right? Can maybe someone not?
Yes.
Okay, thank you. So thanks a lot for the very, very kind introduction, Michal. As Michal said, I'm going to present here our new MLr3 Pipelines project and how to create efficiently pipelines for machine learning through that package. And I'll also talk a little bit about how that nicely connects to the very, very popular field of AutoML, and what our plans are with regard to AutoML for MLr3 in the future. And as Michal has already said, I'm a professor here in Munich at the LMU. I hold the chair now of statistical learning and data science. And what I really should emphasize is that this is really not mainly my effort that I'm presenting here, my work. It's really mainly Martin's work and Florian's work, and MLr3, like the basic package that all of this builds upon, is mainly now Michael Lang's work. And there's also other people like Jakob Richter and Patrick Schratz who have invested a lot of time into the project now. And I think that MLr3 now has become so much better than its predecessor. It's really a result of that group effort. So let me dive right in. So I guess most of you might have heard about MLr2 before, and MLr3 is simply its not its predecessor, its successor package. And as MLr2, MLr3 provides an interface to quite a lot of machine learning algorithms, mainly supervised stuff in R for training, predicting, resampling, and tuning, and benchmarking these algorithms. And we have decided for this third iteration of the MLr project to kind of split up the project into smaller subcomponents. Like I said, I want to focus here mainly on our pipelining framework. Before I do that, at least I want to use about, I don't know, 5 minutes to introduce the basic thing. So there's a, well, kind of the whole universe is also called MLr3, but there's also an MLr3 package. And that MLr3 package is mainly developed by Michael Lang, and it does exactly this here. So it kind of ends after training, predicting, resampling, and benchmarking. So you can cross-validate a couple of algorithms on a couple of tasks with it. And I want to introduce the unified API of that package now through one or a few lines of one example and a few lines of code. So what you usually do in MLr3 is that you organize your data in tasks. So as in MLr2, a task is mainly a wrapper around the data with some meta information. All of the objects in MLr3 are R6 objects. So we really use R6 for a clean object-oriented approach in the whole project. In order to simplify API a little bit for users, we have a little bit of syntactic sugar going on. So you can do, for example, something like this here. This TSK grabs an example task of MLr3 from a dictionary. So most of the interesting objects of MLr3 are organized in dictionaries that you can query easily. So here we take the iris task out of the dictionary. Out of the learner dictionary, we take a ranger classifier, so random forest. And now we can run this random forest here on that task and train it. And this simply changes the state of this R6 object now into a, well, trained object, which means the model slot of this algo object here is filled with the trained underlying object. We can now use that model to predict new data. We can either pass in a data frame of new observations, or you could also predict on the task on this guy here by referring through a vector of row IDs to the observations that you want to predict on. And then you get back a, well, I should probably not say data frame all of the time, because MLr3 mainly, well, it works also with data frames, but we usually prefer to organize everything that's a tabular structure as a data table. Of course, you very often don't want to do this manually here, training and prediction. Now you want to have convenience functions for resampling, like cross-validation. So again, you can pass in your task, you can pass in your learner, you now pass in a little description object for a cross-validation. By default, this would be a 10-fold cross-validation. And then you can run this here, you can resample this, and you get a nicely organized tabular result back from the resample function, and that you can aggregate with respect to a specific measure. So maybe that's a difference to MLr2. We're not like creating, we're not evaluating and scoring predictions in the resample function. So this basically only builds the predictions during the cross-validation. So you get 10 prediction objects, 1 per fold of the cross-validation, and now you can aggregate and score with respect to any measure that you like. So in this instance here, we're using the classification accuracy, and you get back a score for your ranger model on this iris task. And I guess the final piece of code, so that's kind of the most complex thing I guess you can do with the basic MLr3, is running a benchmark. So a benchmark means you pass in a list of tasks, you pass in a list of learners, you pass in a list of resamplings, and that specifies, in this case, through a cross product, all of the experiments you want to run. So in this case, we are running both these two algorithms here on these two tasks, which defines, well, 4 experiments, and we are always using a 10-fold cross-validation. This is also a little, change we did with respect to MLr3. So I wasn't exactly correct here. So you're actually a bit more flexible. You don't, you're not only allowed to pass in these lists, and then a cross product is automatically created for you. What you actually are allowed to pass in as a data table that defines all of your experiments. So you could also kind of create an irregular setup. So in this design data table here, you have 1 column for the algorithm, 1 column for the task, 1 column for the resampling. And if you want to, you can manually set this up as you like. Of course, many people still want to run this exhaustive type of thing. So run everything on everything. And then you can use this benchmark grid convenience function here, which creates this data table that describes the experiments for you. And then you run benchmark, and that executes the experiment now, or the experiments, gives you back a nice container object of all of the results. And again, you can aggregate and inspect now how well these algorithms work on the various tasks. So I'll stop here because this shouldn't, I guess I now use something like 6 to 7 minutes. So I won't show many more examples for MLr3. We have a pretty extensive documentation online and many examples. If you're interested, just have a look at that. And I'll now move over quickly to pipelines. Before I do that, maybe a couple of words on our design philosophy, how MLr3, but not only the basic package, everything else that derives from this, are created, because I think that's important to kind of understand the feel of the project and the ideas behind it. So before we used S3 a lot in MLr2, we have become now over the last 1 or 2 years rather big fans of R6, because we think that this really allows proper object-oriented programming now in R for the first time. We really create classes where data and methods live in the same object. We make heavy use of inheritance. And we also use reference semantics quite a lot in order to become memory efficient in our container objects. We also embrace data table very heavily. So maybe also in a not super usual manner. So of course, I guess you all know that you can represent normal data in a data table, like the data that we work on as data scientists and machine learners every day. We do that because data table is super fast and has 0 dependencies. So we like this a lot. But we also use it in a maybe less usual manner where, well, most of our internal result objects or exposed result objects, as for example here, this benchmark result, right? Where you see, hey, on this task, I applied this learner, I got that result. That's also a table, right? You have different lines that usually encode or represent experiments or repetitions of things. And then you have columns that represent objects and data. And we also use data table for that. And we use one specific feature of data table, and these are list columns. So very often in these complex result data tables, we have references of our 6 objects in there. And that works very, very nicely together with data table. If you haven't seen this before, I heavily recommend looking into this, because this helped us a lot to clean up our container object structure. So one thing that's really nice about MLr3 is that nearly every result object looks in the same manner. So resample and benchmark, they all return kind of the same thing, and we reuse that heavily. So you don't have to learn a lot of new object structures. And as it's a data table, you can use data table programming on top of those. And some of you might be very much used to that, so you can very efficiently program on these. Last point, and that's maybe a little bit also kind of a difference if you compare us to all of these new efforts also in machine learning in the tidyverse. So we aim to be very light on dependencies, because we think that has quite some important advantages for practical work. So we really, really, really evaluate very precisely whether we want to draw in a dependency into the project and, build upon this or not. So most of our basic stuff only relies on R6, on data table, on the metrics package, on this quite nice logging package here. And then the rest here, which is also very small. And this is basically the full list also of recursive dependencies that makes MLr3 very quick to install. And what's, I think, even more important, I hope you also become much more robust because of this. Because, I mean, as always in open source, things change, right? Sometimes API changes, and that very often breaks stuff. And we have kind of suffered from that fact over the years quite heavily. especially in MLr3. Yeah, so this is how the current ecosystem looks like. As I've said, we have decided to split up the project quite heavily because we also think that this allows maintaining the things in a much cleaner and more efficient manner. We also hope that it encourages, well, the community to look at these things a bit more, because it's much easier to look at like a bunch of smaller packages or one small package that is of interest to you than a super large package like MLr3 was, where everything is in there simultaneously, like complex tuning, wrapper algorithms, and so on. So MLr3 had really a couple of 10K-ish lines of code. And I think many people were therefore also, I don't know, scared of looking into it, doing PRs for this. And it was, I think it was confusing for nearly everyone except for me, because that thing I really wrote, yeah, I wrote most of it, I guess, which is now fortunately not true anymore for MLr3. So these green things here are the packages which are now quite stable. So let me, yeah, okay, I guess that holds true for MLr3. The basic package, of course, here we have the pipelines package that I'll present today. Today I'll talk a little bit about our tuning package. Here we have a package to represent parameter spaces, MLr3DB, another effort by Bischl, which is really nice, which allows MLr3 to work on data that's not in memory anymore, but in databases. Also a metrics package from us, which builds upon metrics. And then also important here, I guess many of you are interested in what learning algorithms can you use together with MLr3. We have this MLr3 learners package now. That's also kind of a change in design that now only contains roughly a dozen algorithms that we like a lot, that also I think are pretty standard in the community, like Ranger or like XGBoost or GLMNet. And this lives on cron. And then we have a GitHub org where like little pieces of wrapper code are maintained for all of the other algorithms. And we are currently also investing a lot of time into making this larger and larger and larger and larger. And already there's now quite a lot of extension algorithms available here. And it's just much more, I don't know, flexible and convenient for us to maintain these little pieces on code on GitHub. And that also encourages people much more to help with providing extra pieces of wrapper code to include more algorithms. Okay, let's now really start with pipelines. So I guess, as most of you know, machine learning, especially nowadays, is not just applying ML algorithms directly to data and then kind of be happy because the result is already perfect and ideal. We all know that kind of quite the opposite is true. Like most of the performance that you get out in practical machine learning project often relies on stuff like preprocessing, feature extraction, feature selection, missing data imputation. So all of the practically relevant data nowadays in data science and machine learning is quite quote unquote dirty. And so we have to first often clean it up in a technical sense. So that might be something like, I don't know, scaling and imputation and so on. And then often the real value is in intelligent feature extraction. And although deep learning exists, that doesn't solve this completely. I guess everyone who has practical experience in ML nowadays knows that too. Although DL is super interesting and exciting, there's still like many tasks left where you have to do where classical machine learning is a bit more appropriate, and then you really have to deal with all of this feature extraction and so on. And then there's also, of course, this field of ensemble methods, model averaging and stacking and so on, that often counts for like extracting the last epsilons of performance improvements out of complex tasks. So, and as I explained, MLr3 is basically there to do this basic model fitting without any preprocessing, without any pipelining. And MLr3 pipelines now helps you to represent stuff like this, where, for example, you have a linear pipeline where first of all you do a scaling of your features, then you do some factor encoding of your categorical variables, because very often either your ML algorithm can only deal with numeric features, or you could improve performance by doing some intelligent factor encoding. then you might have to deal with missing value imputation. And then at the end here, you apply your single learner. And I'll show later also how to extend this to nonlinear graphs, to nonlinear pipelines, and also ensembles that consist of multiple learning algorithms and not only one. So what's kind of the abstract structure now behind such a pipeline? And I can already kind of warn you that so MLr3 pipelines might also, another name for MLr3 pipelines might also be something like MLr3 graphs. So we think that being able to represent also nonlinear stuff is quite important and exciting and much more flexible. So our pipelines are made up of two building blocks. So kind of what is happening, how is data, how are data or how are objects processed in a single step. And this single computational unit we call a pipe op, which is short for pipeline operator. And then these pipeline operators, they are obviously connected, right? So maybe this guy here does the first step of preprocessing, and then it sends out its results to this pipeline operator here and this pipeline operator. And this is kind of the way that now information flows through the graph until we have finished our computation. And this is here kind of our end result. And you can already kind of see from the schematic picture here, another name for a pipeline operator in an abstract sense might also be node. And these are edges, right? So what we are effectively talking about here are direct acyclical graphs. And this is exactly what we are using to represent pipelines. And I guess many other, especially modern pipeline frameworks converge to a very, very similar structure nowadays. Okay, so first of all, let's understand how such a pipe op now works precisely. So I'll use here a very, very simple example. We'll use data scaling because I guess every one of you understands intuitively how that works. So this scaling operator is supposed to scale every numerical feature from a data frame by, for example, subtracting the mean and then dividing by the standard deviation. So, and what I want to motivate here is that these pipeline operators, yeah, so how they work is actually not that much different to how a machine learning algorithm works. So the important thing to note here is that it's not a single function, it's actually two functions, right? So it has a training part and it has a prediction part. So every pipe operator has a training method, and that training method usually accepts a list of objects, and it's supposed to also transform it into a list of objects during training. And the same API signature is also true for prediction. So always a list goes in, a list goes out. Many of the operators take lists of exactly one element and return one element. And for many of the operators, also this one element is a data, is a task. So often tasks go in, tasks go out. Yeah, especially holds true for all of this preprocessing and feature extraction. And the same is also true for the scaling operator here. So training data goes in, then the scaling training function is being called, and that is supposed to also now output transformed data. So this would be a scaled version of this guy here. But what also happens during this training procedure is that we have to store parameters. So we really learn something from the data. For scaling, we just learned something that's very simple. We learn these scaling factors. Yeah? So maybe this is a list of mean values, one per column of the data frame. And we also learn the standard deviation. And the reason why we have to learn those and store those is because during prediction, we are now only supposed to apply what we learned during the training step, right? So now, again, data goes in. We are supposed to transform it, but we have to use the parameters that we picked up during training. So we use these scaling factors now and simply apply them. You can also see how this works in terms of code. So here you have this syntactic sugar, this PO, which is short for pipe operator that again accesses a dictionary in MLr3. It takes out this scaling pipe opt. Now you can train this. You can see here how you input a list of a task. you can also now have a look at how this, how the output looks like. You can see this is also, again, always a list. And this list now consists, or this one element in the list is now a task, and we can simply peek into the head of that task, and we can see here that this is a transformed, scaled version of our well-known friend, the iris dataset. You can also investigate how the learned parameters look like. So every pipe operator has a state. In the beginning, this state is simply null because the object is untrained. But after we have trained it, you can see what's in here. And that, of course, now depends on the operator you applied. And because this is scaling, you can see exactly what I explained before. So the center values are stored here, and these scaling factors are stored here, which are then later on applied during prediction, which is what I'm doing here. So here I'm just doing a little bit of filtering for our task. So my result actually fits on the slide. So I'm just filtering down the task to 3 observations. So I only have to display 3 predictions. I guess it's now interesting to summarize a little bit what we have available in MLr3 pipelines at the moment in terms of functionality. So there's a lot of simple preprocessors available. So scaling, Box-Cox transformations, U-Johnson, PCA, ICA, and so on. We have quite a lot of missing value imputators present, especially univariate ones. I guess we can become a little bit better in terms of multivariate imputation. So there's constant imputation, histogram sampling. Yeah, there is some model-based multivariate imputation, dummy encoding. We have quite a lot of categorical data encoding, so the usual one hot, but also more interesting stuff like impact encoding. A little bit of text processing. Actually, I think Florian was also responsible for including that. Feature filtering. There's a specific extra package, MLr3 filters, that's connected to MLr3 pipelines. So that allows you through statistical and information theoretical filters to deal with high dimensional data. And then we have meta operators that allow stuff like feature union, branching, ensembling, and stacking. These are more complex things. I'll show them later in examples. And we also allow not only changes of the X column, you can also do target transformations. So I guess the most relevant thing here is stuff like log sampling in regression, where you want to rescale your Y. So it potentially becomes a bit more balanced and closer to a Gaussian distribution. Okay, so what operations are now possible to connect these pipe operators? That's kind of the exciting stuff, right? How can we form from these atomic elements now complex graphs? So the most important operator is this concatenation or pipe operator here that takes 2 pipe ops and then splices them together by connecting the outputs, or I guess you could also say the sinks or the right-hand side of this partial graph here with the inputs or sources, or the left-hand side of this second partial graph, and it splices them together, as you can see here, and forms one larger graph out of this. There's also another very simple operator, which we call G-union for graph union, and that simply takes multiple graphs or multiple pipe operators and also connects them in it, or sorry, not connects them, merges them to a single graph without doing any connection. Yeah? And let's now apply these operators to construct some simple examples for linear pipelines first. So how about we, again, have a look at this example that I presented before. So scaling, factor encoding, median imputation, and then using a simple machine learning algorithm. How would that look like? Well, you simply do this PO operator. You grab the scalar, you grab the encoder, you grab an imputer, you grab your learning algorithm. And here you can again see that we are using a little bit of, I don't know, syntactic sugar. So if you create an MLR, so there's actually a pipe operator that wraps a learner. And in order for you not to have to write this down all of the time, there's sometimes a bit of upcasting going on here. So if you write down an MLr3 learner that's upcasted to a learner pipe op automatically for you. And this you can now concatenate together to construct such a linear graph. And we can also now train a complete graph, and training a complete graph is, I think, much more interesting for users than training individual pipe operators. So how does that work? Well, you simply call the train function on your input task. And what happens now is that data propagates through the graph during the training stage. So we move through these individual pipe operators. Their training function is called internally. The pipe operator state is being learned during this training call. And we propagate the output now of this pipe operator. So the result of the pipe operator training function to the next operator. And do this again, learn more parameters, propagate the result, learn more parameters, propagate results until here we end during the training stage. Nothing more is really outputted, but we store our model here in that last node. And now during prediction, again, we now pass new data through the graph. And the only difference is that now we call the predict function of all individual pipe operators, and we apply these trained states, and data propagates through. And now we have formed an output object, which is a prediction object. Okay, a little bit more technical stuff. So how can you now access these graphs? Is that difficult? No, it's not. So one thing you have to understand is that each graph contains as one member variable a list, which is called pipe ops. And this list is named. And what I should have maybe said before is each pipe operator has an ID. So it has a default ID. So the scale pipe op is called scale, but you can simply manually override this and set this, define this during construction. And now this here is simply a named list. And you can simply point to or grab a pipe operator out of this by its ID. And you can now access this in a super simple manner. As long as you remember how your operators are being called, how they are being named, you simply can get them out of this list. And what you can see, for example, here is how you can set the parameters, the hyperparameters of a pipe operator. That happens exactly in the same manner as it happens for MLr3. So this is again here a named list of values where you, for example, now can set the center hyperparameter of the scaling pipe op and so on. You can also receive the state. So it's exactly the same structure. You kind of reach down into this list by name, you access the state, and you can see now and inspect the internal state. That's maybe not so interesting for practical purposes to really compute stuff, but it's interesting for debugging, right? So maybe something goes wrong, or you just want to learn a bit more what happens in your pipeline. And we also store intermediate results. So the stuff that's like computed here and here and here, when data is or objects are propagated through the graph, we don't do this kind of by default, but we store it there through memory. For memory efficiency, we kind of delete intermediate results, but you can simply set a debug option and then access this dot result thing here, and can also inspect what's computed in every step. Of course, as I said, we now can also create nonlinear pipelines to create more exciting stuff. So the important operators here are branching, copying, that's often not necessary anymore nowadays, I guess. Feature union is pretty useful, and model averaging. So how does that work? So how about we now create a random forest ourselves with just a few lines of MLr3 pipelining code? So how can you kind of abstractly define what a random forest is, or let's say a bagged tree maybe, to be really precise. So that consists of a subsampling operation where we subsample the rows and then we fit a decision tree, right? And we do this multiple times. And at the end, we do some majority voting. And you can write this down with MLr3 pipeline code by having this partial graph here where you first do subsampling and then you do, for example, an R part. Now, here's a little piece of convenience code, which I'll explain later. So that kind of creates partial graphs. So that's kind of an idiom that you can use to construct interesting partial graphs. And for example, here's this idiom greplicate that takes a partial graph and then simply replicates at n times. So now you're constructing this guy, and this guy here without connecting them. But I will now concatenate them together, their endpoints with the majority voter, and now I've created a bagged tree of size 3. And of course, you could just set n here to 100, and this might be a more realistic version now of a bagged tree or nearly a random forest. And this is, I guess, 2 lines of code. Well, maybe 3, depends a bit on how you force me to write the code on a slide. And yeah, this is how data would flow through this in such a nonlinear structure. I guess this is also pretty intuitive and plausible. We can also do stacking. So we can, for example, take a linear model. We can create an SVM, and I should actually say here that we're not really creating a basic linear model and a basic support vector machine. We're actually putting them inside of a cross-validation node. So as some of you might know, if you do stacking, you really want to kind of combine cross-validated predictions and learn on them. We even can do something like adding a null node here. So this null node simply passes along its inputs. So in this case, the input task is simply passed along. And what happens now here in this feature union node is that the cross-validated predictions of the linear model are C-binded together with the predictions of the SVM, and they are C-binded together with the original features. And I now put a second level model on top of these predictions and on top of the individual features. So I can now stack these things together and even kind of decide, depending on where I am in my input feature space, whether I'd rather want to use the linear model or the support vector machine. And you can write down this pretty complex stacking model. I guess some people also call this a gating model, yeah, where you are allowed to also act upon the input features in these few lines of code, yeah, even with integrated cross-validation. Here, a quite important concept for AutoML later, that's branching. So what branching allows you to do is you have this node here, and this node now allows you to control the flow of information in the graph. So you can set a hyperparameter that says go up or go down or go to this specific next node. So information only flows now along one branch or path, you might say. And then here in the unbranch, we technically kind of merge paths again together. So you can create this like this here. You can create this pipe operator for branching. You can specify like how these paths are called. Then you concatenate this together with the PCA and then the ICA, and then you unbranch. And at the end, we concatenate this, for example, with the KNN learner. Again, well, I think this is already short code, but we made it even, I guess, shorter. So there's also this PPL idiom available where you just say PPL branch, you list your pipe operators, and that's already it. That kind of creates this thing here automatically for you, and then you concatenate this with the KNN learner. And what I skipped before, the important thing now is that if you look at this pipe operator and this branch at this pipe operator list, and here inside of that you have this branch element that now has a selection hyperparameter. And this selection hyperparameter you can set manually if you want to. And now you can control that information only flows along this path, or you can set it to ICA and then it only flows down here. So of course, we really don't want to do that manually, right? What we want to do later on is through hyperparameter tuning and an AutoML learn what is actually best for our data set at hand. So maybe you have like different feature extractors going on here. Yeah. For example, PCA or ICA, our different pre-processing options. Yeah. And you simply want to learn in a data-driven manner which of these work best with respect to a cross-validated score. I think I will skip this nearly. So this is just a little technical extra section where we demonstrate to you that you can also nicely configure your pipe operators so that they are only applied to certain subsets of columns in your data. So this is easily configurable. So all of these pipe operators allow through this effect column thing here that you can specify patterns. For example, you can even use a grep on the name and then say, hey, I want to just apply this PCA, for example, only to these first two columns because they start here with the sepal prefix string. And that would apply the PCA only to this part of the iris data set. And there's a lot of these selectors available to you that you can use to apply your operators to parts of the columns, and that makes the whole thing just that much more flexible. And there's a second alternative. There's this pipe op select thing, that allows you to do a similar thing, but really now through a pipe operator and through an argument of a pipe operator. Like I said, I'm skipping through this now a little bit more quickly to come to more interesting stuff. So I've mentioned this PPL thing a bit. So this is a pretty new. We haven't created too much here, but already a few things, and we think at least that the concept makes sense. So very often you have like frequently used patterns in pipelines, and you might get, I don't know, fed up with having to write them down again and again manually. So for example, we like making our learning algorithms more robust for bad data, for practical experiments. So very often we end up with kind of doing the same thing to robustify this thing. So some basic imputation, some basic feature encoding, some basic handling of, hey, I'm seeing new levels at prediction times and I don't want my algorithm to crash. How about if there's like a little like convenience call available to me so that I can do this just with a single function call? Or for example, bagging is a pattern or branching is a pattern. And we now have begun to organize them also in an MLr graphs dictionary, where at the moment, like I said, there's only a few of these patterns now available, like this robustify here, which does something like this, or target trafo. So this is like where to achieve a certain feature, you have to write down a couple of nodes, and that, you might want to do this in a shorter manner. So for example, you could now have a look at what does robustify actually do. And as you can also see, you can now plot partial graphs here. So robustify, for example, does some imputation through a histogram. It also stores indicator columns for your, so dummy columns for the stuff that you imputed. And then there's some handling of new levels going on. So this is all like robustifying categorical variables, specifically unbalanced categorical variables, and then encoding and so on, removing of constants. And you can now nicely visualize what happens here with the partial graph. Or like I said before, it might be a little bit annoying for the branching to have to technically write down here this beginning of the branch and then the unbranching. So as I demonstrated before, you can simply write down PPL branch and you list like the two pipe operators that you want to have in there as options. And these don't even have to be pipe operators. You can even put in here partial graphs, so longer sequences of operations, and branch over those. I guess I'm surprisingly fine in time. So let me now spend the remaining 5 to 10 minutes on what does all of this has to do with AutoML. So what do we mean if we say AutoML? It's, in a certain sense, it's a more fancy name, I guess, what we meant before when we said hyperparameter tuning or model selection. I guess what is an important aspect of AutoML is that we are now often not optimizing over single machine learning algorithms. Well, we are optimizing over pipelines, right? So we really want to make an automatic optimization procedure now make decisions about what learning algorithm to use, what preprocessing to use, and how to configure these things. So some of these decisions are decisions over, well, how to set certain technical parameters, so how to set configurations, but like what learner to use and what preprocessing to use and so on are more like decisions about graph structures, right? So in a certain sense, you could say that AutoML is made up of having efficient optimizers and tuners available. And one algorithm that's super popular nowadays is, for example, Bayesian optimization. And we also work on stuff like that. And then a second component is how can you nicely represent these, hypothesis spaces of your complex processing chains. And that's, pipelines. And what we are now mainly talking about here, although we also love to talk about like black box optimization and Bayesian optimization and so on, we are now here talking about why it's important to have a nice expressive domain-specific language available to you, so you can write down these these spaces of potential models. So yeah, and this you kind of might see as a single line definition of AutoML. Yeah, being able to define pipelines and then being able to do efficient parameter tuning on these. So in an abstract manner, it might look like this. So there's some preprocessing. Maybe you do preprocessing A, maybe you do preprocessing B, maybe you do some feature extraction, and all of these things you have hyperparameters, right? And then there's some, maybe you do now machine learning model A, maybe you do machine learning model B. Again, these things have hyperparameters, and you now have to tune over stuff like which of these things do I actually use, or which of these things do I actually combine, kind of stacked ensemble, and how do I set all of these annoying technical parameters here. And these decisions we nowadays usually make with efficient black box optimization. So one thing I should say is that we are not like as done with this component here as we would like to be in MLr3. So at the moment we have only very quite basic tuners available, but we are investing at the moment a lot of time to also convert the Bayesian optimization stuff from MLr2 into the MLr3 universe. I guess this will be finished, I think, hopefully during early summer. We also have stuff like, maybe some of you know this hyperband algorithm for multi-fidelity black box optimization. That's actually already nearly available for MLr3. So before I'm now showing, I think, a final piece of code is, so how do we actually connect now these graphs to MLr3? I think I haven't also presented that before. I kind of have only shown you how to construct these pipelines and how to kind of directly train on them. But what you can also do is you can easily connect them to the world of MLr3, to the package MLr3, to be able to do resampling, benchmarking, and then later on tuning. I guess that's most important for us for AutoML. So you simply write down your pipeline as I've shown to you before, and then the only thing you now have to do to connect to everything else in the MLr3 universe is you put this into a graph learner, and this allows you now to kind of access this guy here as an MLr3 learning algorithm. And after that, everything feels exactly the same. So this pipeline feels exactly the same API-wise as, I don't know, a basic learning algorithm, as a basic decision tree, as a basic random forest. You can train the pipeline, you can predict the pipeline, you can resample this, you can use every operation from MLr3 that I've shown before, and you can also use MLr3 tuning. So don't have too much time left to explain how that works, but MLr3 tuning is our framework package to do any type of black box optimization, either on basic learning algorithms or pipelines. So what that does is you define a search space, you pick a certain, you pick a performance metric you want to evaluate, you pick a protocol, how to evaluate the performance metric, something like cross-validation, and you pick a terminator when to finish the optimization, and you pick an algorithm, a black box optimizer, and that now runs here such a continuous loop. It always suggests new interesting configurations. Yeah, these are tried out in your design space, you measure performance, and then hopefully you have picked an intelligent algorithm that helps you to optimize the configuration with respect to its measured performance over your budget. And at the end, you return the best configuration you have seen. And in a certain sense, you're now learning hyperparameters on a second level in a data-driven manner as you're learning basic parameters in ML through risk minimization. So it's kind of the same principle, just on a second layer. I guess the last thing I want to show to you, hopefully in the last 5 minutes, I should be able to cover that, is how can we now kind of write down a quite maybe complex, nearly AutoML system from scratch with MLr3 and MLr3 pipelines code and MLr3 tuning code. And that's actually not that difficult. So for example, maybe we first of all want to make a decision whether we want to do feature extraction through a principal component analysis or simply leave our features as they are. And we don't know what's better. So we use a branching template here to have this forking at the beginning going on, either PCA or leave features as they are. And then maybe our our original task is quite high dimensional. So now we want to filter features down, maybe through such an ANOVA filter. And then after we have filtered down our feature space to a smaller dimensionality, we are now not sure which algorithm to use, right? As always in machine learning, we don't really know how well stuff works unless we have tried it out on our data. So how about we just have the AutoML system make that decision? So maybe we want to try out an RBF SVM, maybe we want to try out our good friend XGBoost, or we want to try out the really robust Ranger random forest. So we again have this branching template going on that now allows us to pick in a data-driven manner one of these three algorithms. Now we pipe all of these together. We call graph learner on the thing, and now we have connected the thing into the MLr3 world. It's a real learning algorithm now, quite complex one. We can plot this, check it. I guess that's even easier to understand than the code, right? Here you can see what type of preprocessing or as feature extraction to do first. Here you can see the filtering. Here you can see the three learning algorithms. And after those are being applied, you now have a potential prediction available to you. And this now has quite a complex hyperparameter space, and we can tune over that. So first of all of these branching nodes have a selection parameter here, yeah? And you can now select either do PCA or nothing. This ANOVA filter has a fraction parameter. So how many features should it let pass? Like 10% or all of them. Here you have the second branching operator that has levels SVM, XGB, or random forest. And then here all of the hyperparameters for the random forest, for XGBoost, for the SVM. We only chose to write down a couple of these. You can add just 5 more lines if you wanted to. What is a little bit more complex than what we like is some of these parameters are now of a hierarchical structure. So for example, this random forest M3 parameter only makes sense if we are selecting also the random forest in the branching. So we have to add in this dependency statement. This is actually something that we are a little bit dissatisfied with at the moment. This stuff should be auto-generated. And I think this page here, I think if you read the documentation, it's very clear how this is constructed. But I find this a little bit verbose. So I kind of want to figure out whether there's maybe a shorter, better, syntactic sugar type of language on top of this. So we can abbreviate the stuff. You can also see here that you can do stuff like parameter transformations. So for example, most of you will know that these SVM parameters, so stuff that goes from 0 to infinity, like regularization parameters, or kernel width parameters, are usually optimized on a log scale. So you can also do something like that. And now you can create something like a tuning instance, which puts together your black box optimization problem. So you say, hey, let's maybe optimize this on the sonar task, use our graph learner here, do a 3-fold cross-validation to measure performance, measure classification error, set the terminator to 10 evaluations. So I can run this for the slide set. Probably should be a bit longer for practical applications, and also put in here this feasible set, our search space for optimization. And now we can pick a tuning algorithm. So for example, simply just random search, because that often still works well in AutoML. And then we can tune this and get our result. And also, as I said, I didn't have that much time here to talk about MLr3 tuning and all of the stuff connected with it. Of course, you can also just add one extra line in there, and then you get true nested resampling on this and unbiased performance estimation, which we all know is also important for practical work and estimation of future performance. I wanted to keep it a bit simple here and didn't add this in. It's basically one extra line of code, and it works even easier than MLr2. Okay, that's it. Okay, maybe 45 to 50 minutes. I hope you had enough patience to listen on. So I'll conclude with how can you learn more? So there's an MLr3 book available. It's not completely done yet. It's really an online book that's growing over time. But I think it's probably a good, nice resource if you really want to study the package in depth. If you don't have that much time available to you and you want to kind of peek into the package quickly, start with our cheat sheets. So we have a cheat sheet for MLr3, one for MLr3 tuning and one for MLr3 pipelines. this is a good reference. Yeah, I mean, I guess you know how cheat sheets works, right? And why they're valuable. If you really want to get like a 10-minute introduction to the package through a use case, have a look at our MLr3 gallery. That's also pretty new. It's growing, but there's a lot of use cases and demos there. So you can kind of understand how the package works through simple examples. So for example, I wrote an how to use MLr3 on Iris thing, where I guess you can understand how the package works in 5 to 10 minutes. And we also have quite a few more complex things on there for pipelines. Thanks a lot. I hope that wasn't too long. That's it. And yeah, as I said, what's going to come in the future? Better hyperparameter optimization, some technical extensions for pipelines, especially want to improve caching and parallelization and so on, and just robustify the whole thing a bit. But at the moment, I would say it's very, very much usable already. And we are using it already, a lot of applied tasks and papers. Now I'm really done. Thank you.
Bernd, thank you very much for this great webinar, great presentation. I must admit, new MLR looks really sweet. Honestly, in my heart, I miss all the good old times when we were using functions like generate trash versus perf data.
I don't miss these times too much. Yeah,
it really does look different. So aside from being light of dependencies, what are the major design decisions behind MLr3? How could you sum?
I tried to do this a little bit here on this slide already, but well, I guess one of the most important design decisions was split everything up. Yeah, so I was just too scared to do this for MLr2 because admittedly, it's still much more complex now to kind of maintain the thing on CRAN. Yeah, but I think it was very worthwhile. I think that was kind of the most important decision to split it up, because that really influences a lot how you can kind of cooperate together with a larger team. And MLr3 really wouldn't exist if I would be the only main programmer. And it's now about 10 persons, I would say, that really put work into this stuff here. And without this splitting it up, that wouldn't be possible. And then the other decisions, R6, and it's especially this combination of R6 with data table and being light on dependencies. So I mean, in terms of like programming patterns, really R6 together with like organize references and tables.
Thank you. So we have in our audience judging from the questions, quite a few of MLR fans, and they are very curious. So we know that still not everything from MLR is imported in MLr3. So if you would you be able to give us firstly a quick overview? What are your priorities in implementing? And secondly, do you have any schedule when the things will be implemented, or is it just done when it's done?
Well, I guess I can try to answer that. So, I mean, what's important to understand is that, I mean, the project is still kind of, I don't know, run a lot by like goodwill of persons, right? We are being funded a lot. So in a certain sense, I mean, a lot of the stuff is being programmed like people like Florian and Martin and so on, who are PhD students and who of course have to do academic work and kind of, yeah, have to work also on improving their CVs and their publications. So that makes it sometimes just obviously a little bit harder to kind of schedule against. So we don't really, well, what we try to have organized stuff and prioritize stuff through like core meetings and core calls. At the moment, the highest dependency is, thunderstorm is starting here in Munich. So the highest priority currently is this branch here down here. So making tuning better. At the moment, this is just not good enough. I want to have a true Bayesian optimization. I want to have more technical infrastructure below all of this. So at the moment, we are putting a lot of resources on this. Martin and Flo are still improving pipelines a lot because this is super high priority, because I think this will be most useful to people in practical work. So at the moment, make this a little bit better. and make this year a lot better. That's the current schedule, and this should be done over summer, hopefully a little bit earlier. After this, I'm actually not super sure what will come next. I guess either here this probabilistic learning or the forecasting. So for this, we are really looking for people who can help us working on that. We are lacking a little bit of resources here, but we think this is super important for many users. Florian has already invested a lot of work here, but as he's also working on pipelines, so if there's actually people interested in this, I think this would be very important. I was always very unhappy that MLr2 was so bad with this. We are looking heavily at how the guys with SK Time are structuring their project, and we think we want to implement something very similar.
It's really great that you mentioned forecasting, Bernd, because actually we have a question in chat about the forecasting, and maybe Florian could give us a bit of insight on this. So how would the do you plan any, aside from the functionalities from the old MLR, do you plan anything new for the forecasting in or maybe functional analysis in the MLr3? How and in the MLr pipelines?
Well, yeah, I guess you can hear me?
Yes.
Yeah, fair enough. So we implemented, or we started to implement MLr3 forecasting as a student project. And it's currently in a, let's say, so-so state, but it's also being developed. So there are some preliminary algorithms available, and you can sort of start to play around with it, but I wouldn't say that it's very comprehensive. But I think this will develop in the future. And also, I would like to invite everybody who feels like he or she wants to participate to sort of check out, make issues, or just create pull requests or talk to us. We would be glad to have collaborators there as well.
Maybe one important thing to mention, so if people actually want to talk to us about stuff like this, we have a very, very active MetaMouse server. The best thing is just, and we are also pretty open there, just connect to that. There's channels that are open for everyone, and just talk to us there.
So if you would like, Bernd, we would be very happy to put the Mattermost link in the video description for the future. Sure. Great. So another question from the chat: do you have any good MLr3 examples in production environments? And how to serve models? Do you have any, for example, if I want to serve MLr3 model with Plumber, how do you have any syntactic sugar to streamline it?
So, I mean, this is of course something that, I mean, I don't know, in the academic world that we are not looking at very often. I mean, maybe also Florian can comment a little bit more on that. So one thing I want to say, and that is that I'm often, how to say that, quite surprised. So I don't receive too much email. I receive too many emails, but I mean, I wanted to say I don't receive too much like feedback by email, like who uses this. But I very often, so if I go like to certain, I don't know, conferences which are more industry flavored, I very, very often meet people who apparently use MLr3 or MLr2 mainly there. Now also MLr3. I think very often they prototype with it. And then after they've done all of the model selection and the figuring out what works well, then they try to kind of, I think, transfer this into something that's maybe a bit more robust. And also, I guess we also have to be a little bit honest here. Often that's not R-based. But I think that's not, I think that's probably a very smart move doing something like this. So prototype rapidly with something like this, and then yeah, use other maybe technically a bit more mature tools for production. We have been looking into stuff like that, but we really haven't tightly connected it to some of these frameworks. Florian, do you want to add more on this? You're muted, I think.
I guess so. I really wanted to do actually a tutorial on how to productionize our models with Plumber, but I didn't get around to do that. So thanks for asking, and I guess I hope I can do that soonish.
Let this be a motivation, and maybe the next question will also motivate you to focus in a slightly different area. we have representatives of the deep of the deep learning community, who are asking about the integration of MLR and deep learning. And Bernd, please, using this time, comment also. Do you plan any integrations of deep learning frameworks and MLR without intermediate packages like R packages like Keras or TensorFlow? So will MLR3 Keras will be?
I'm pointing already on the relevant subsection of the ecosystem, and I'm refusing to answer this because this is also Florian's project.
Fair enough. So I started playing around with Keras and with deep learning for MLr3. Currently, I guess, so the biggest problem is that I'm basically the only developer, the only one that works there. And the other problem is that, so currently we don't really support anything else, anything other than, let's say, traditional tabular data in MLr3. So we will also need to sort of do some extensions there if we want to support images and make, I guess we need to also make a few clever decisions. So I would really like to welcome everybody who works in that field, who likes to work in that field in R, to also join us and help out there. Yeah, I guess that's.
I mean, I guess I want to correct a little bit about my answer to what's like next on schedule. So I think also for the core team, this is something that's pretty important and we want to get better there. Like on tabular data, I think we're pretty close to having something that's already very nice, but as we all know, it's much less interesting, right? To do deep learning on tabular data, it might be a bit interesting. So what is more interesting is how we can kind of get images and text like directly into MLr3. We have some ideas for this so that like tasks can actually refer to files. Yeah? But this is something I really have to discuss a lot with Michel, how we can extend the basic task structure and API. But I think if you would ask me what's like the most important thing to revamp or improve the basic structure, that's probably it. And I kind of forgot mentioning that. So thanks for asking about that.
Okay, so using my privilege as a host of this meeting, there is always with MLR, I was really compelled by the great breadth of the documentation which is available for the package, and of course the documentation has evolved along with the package. I think the digital book is a great way to do this because it can follow the development. But my question is, are you planning on publishing real DAT3 format books about MLR? Will it happen soon?
You mean like a hard copy printout?
Yeah.
I'm getting very, very many emails about stuff like this from publishers. I kind of, so in the past, I kind of refused doing that because of time constraints. Now I'm kind of, I guess, refusing doing that because I'm not sure whether I see the value of that anymore so much. So if the book exists in an online format, I'm not sure why we should print it out anymore. I don't know if somebody can come up with a super convincing reason why this is so good and great. I guess we might do it. At the moment, I care much more about improving the contents here because I think the format is already not that bad.
Because my impression is that this book carries a bit also about your philosophy on machine learning. So, you know, some parts of this, and so some parts of this really, I think, needs extending. So could we expect any series of MLR related books?
So, well, what I really would like to do is like take something like 2 months off and really finish this. But this is very, very hard for me to do. I guess Florian and Martin are probably now trying not to laugh if I say something like this. I would like doing that. I would just have to fight heavily finding the time. So I have like 2 upcoming sabbaticals. So because I got an extra one. So that there's at least a slight chance that something like that might happen. I would like doing that. But I don't want to promise too much now.
Finishing is always the hardest part of the project. So we have another question from the audience. how could MLr3 framework be used with the big data?
I guess the canonical answer is look into MLr3 DB, and I guess combine this with ensembling approaches. I mean, we all know there's these super simple tricks of just working on like parts of the data using like bagging or subsampling approaches, and have a look into this. I think that's at the moment our best answer. The other thing is, again, the other route would be to extend tasks with respect to kind of the, so, okay, what I should mention is, and I think that's a huge step forward. So look, if you looked into MLr2, MLr2 only allowed you to work on data frames, right? Which means memory data is always expanded in memory, and you can't extend this at all. So now in MLr3, we're using data table. Well, this is a bit more efficient, but in terms of design, that also doesn't help you a lot. The huge step forward is that we abstracted away from this table thing to an abstract data source. So we can now kind of create subclasses for particular storage types of data. Of course, the most important one is still a data table, but there's also a connector to a database. And like I said, you could also write connectors to like arbitrary files and other stuff. This is like the part where we would have to invest more work. But at least the design now makes this possible. At the moment, if you want to try out some like simpler approaches where you don't want to expand your data completely into memory, really look into MLr3DB. So Michael invested a lot of time into this. I think this is badly under advertised at the moment. Let's put it like that. I think most people don't even know that this exists. And I think we have to, I don't know, blog a bit more about it or write examples for the gallery.
Promotion is always
quite a few nice tricks with it.
Promotion is always the hardest part of writing free software. Bernd, so we have already a great framework, a great package for managing frameworks in R, a Drake package by Will Landau. How does MLr3 integrates with Drake workflows?
And actually, so Patrick Schratz, who is also part of our developing team, has actually written, I think, at least one or maybe even multiple tutorials about this. So you can actually integrate this very, very nicely. Just Google this a bit. Patrick has, I think, a quite lengthy blog or tutorial page online where he showcases this. So the short answer is it works very well together.
Okay, so we have.
Well, I'm not sure whether it depends a bit. Let me maybe add one extra sentence to this. So I'm not sure whether I understood the question correctly. So you can like use Drake like on the outside around MLr3 to organize experiments. If the question was like, because Drake also builds upon graphs, yeah, are we kind of reusing that structure? Here the answer is no. We did actually talk to the guys a bit about that, whether we can kind of build upon the same like computational engine on the background. That would actually be super interesting at the moment, except for like some, I don't know, talks over a coffee table. Nothing really has happened there.
I see that we are pretty actively answering simpler questions in the chat. So let me ask another one, another of the broader ones.
So now I have only to answer the complicated questions. That's very
So when MLr started, we haven't. When MLr started, the AutoML was in infancy, but right now the AutoML is starting to be a bigger and bigger part of the machine learning world. So what are the future directions of MLr? So how much further you want to go with the AutoML with your tool?
To think a little bit about this, I think that's actually a really complicated question. So okay, I have to answer kind of in components with regard to that. First of all, I mean, we are interested in AutoML also as scientists. Yeah, so we are really interested also in doing research on like optimization and so on. So we are very much interested in also kind of implementing our work in these more efficient optimizers here. Second component is I do think that kind of AutoML potentially also sometimes goes into partially wrong directions. So when many people who work on these fields now create like complete black boxes that you can't control that much from the outside. Of course, in a certain sense, you could argue that users want exactly that. So machine learning is too complicated and too flexible, and AutoML is exactly the answer to this, where the only thing input into the system is like a budget time, and that's it, and then everything works automatically. I don't think this is really, I think this is a bit naive. So you want to be able to put in a little bit of prior knowledge, a little bit of structure, and also you kind of want to kind of, I think you just have to tell the system a bit about what your goals are. So how sparse should your result be? Maybe you have multiple performance metrics that you want to optimize for. So multi-criteria analysis might be very interesting. So that's actually a topic that we are also very interested in, where I think MLr3, especially in a short time, will be maybe much better than other tools. One thing that I always thought, which is important for AutoML, is what you want to do is you want to be able to efficiently write down interesting spaces that you can optimize over then, and then delegate that to black box optimization. And that's kind of exactly the philosophy behind MLr3 pipelines, and that I kind of tried to showcase in the last code example. So like be able to build variants of such systems quickly, because I don't think that at all at some point in time someone will have an AutoML system and the only thing you input is data and time, and it will always do everything correctly, because I mean, the whole like task of the thing is not even specified then. And sometimes we also have to kind of be able to introduce our knowledge as data scientists and modelers from the domain to the system. I think the whole question is just how efficiently can you do that? And this is something that I really want to work on.
Thank you very much. Our audience is really dying to hear if they are going to convert to MLr3 from other packages for machine learning. Should they start with MLr2, or can they go directly to the MLr3? Is MLr3 mature enough?
MLr3 now. I mean, it depends a bit on. I mean, I think it depends a bit on what type of person you are. Like and what the requirement, what the like the side constraints of your project are, what you want to use it for. But if you just want to, I mean, especially if you are like something like a student, or if you're in the academic world, or if you're trying, even if you're trying out stuff in your job, I think now is the correct point in time to migrate to the new system. That point in time might have already been passed. So I think that was also even the correct answer, like maybe a couple of months ago, maybe even beginning of the year, but especially now, we're diverting all like resources into the development of this year. And I don't think that we are much less stable than MLr2. Yes, some features are missing at the moment, but it's not that many. And the pipelining adds so much extra stuff on this that it, I think, kind of immediately counterweighs that. I can't come up with too many things where MLr3 is that much lacking. If you really need like super efficient Bayesian optimization, Martin even has wrote a wrapper, so you can use MLr2 MBO together with MLr3. This is technically a little bit hacky, but even that's possible. And I think that's currently the biggest like downside or like gap that's out there. So really don't stay with, I only stay with MLr2 if you have like thousands of line of code depending on that API.
Thank you very much. So MLr was always known as a tool very friendly for high performance computing. The parallelization was always amazing since the first version of the MLr, thanks to also Michel Lang. My question is, how flexible is parallelizing with the pipelines? How do pipelines affect parallelization?
Okay, let me answer not exactly the question, but another one first, because I think I didn't mention that at all during the talk, and this is a super important topic. So I'm not sure whether we invested a lot of time in MLr2 in making something like this good. I think what we didn't do correctly was that we kind of created a lot of code ourselves. That the reason for that was also because some of the nowadays very popular parallelization frameworks in R weren't so mature at that time. Nowadays, we are super big fans of the Futures framework, and we have decided to kind of throw away all of our own code except for batch tools, and batch tools is already connected to Futures. So even for that, we didn't have to do anything. So we're just delegating directly to Futures, and the whole parallelization of MLr2 is therefore not only much cleaner, much more configurable, it's also in a certain sense more efficient, because we can kind of write down especially benchmark experiments in a much like more flat manner, and yeah, parallelize more efficiently over this. That's the answer for MLr3 itself. For pipeline execution making, I think parallelization doesn't matter that much. So the direct parallelization of the pipeline itself doesn't matter that much if you don't have super large pipelines, because then you rather want to parallelize over the cross-validation or over the hyperparameter optimization. Nevertheless, we still want to make this better, so you can directly parallelize like the execution and the computation in the pipeline itself. But I think that this is I think only relevant for people who are constructing really large pipelines with MLr3, and I would guess that that not that many users exist. Martin, do you want to add something here?
Well, we are in the process of building parallelization into the graph, which would make it possible to have, well, more fine-grained parallelization, even if you have one big execution that you want to have run on multiple cores. And, well, make use of the computation. Well, in that sense, the graph would actually become a computational graph. So you could actually represent the things you want to parallelize as a graph and have parallel paths for things you want to have run in parallel. But as Bernd said, if you use it for machine learning for tuning, which are usually the things that take the longest time, you want to parallelize on a different level usually.
I mean, if I can add 2 more sentences. So I mean, I really want to advertise Future. So if some of the persons in the audience don't know that package that well, I heavily recommend looking into that. It's great. B, some stuff that I actually would like to work on a bit more is more like asynchronous parallelization. I think that's quite important, especially for tuning and AutoML. At the moment, we don't have anything there yet, but this is also something I would like to look into more.
Okay, so before we go to the next questions from the audience. Bernd, if you would have to start, if you would have a chance to start working on MLR once again, with your what you would do differently? What was the biggest mistake of the? What was the cardinal sin of the first MLR?
I mean, well, I mean, you're asking me if I would now start differently. I think, I mean, we exactly kind of went through that question and asked ourselves that question about, I don't know, exactly 1.5 years ago when we created MLr3. Kind of our answer is this now here. I'm not too sure. So at the moment, fortunately, I can't point to many design flaws of the current project. Well, I mean, if you want to ask me what did I do wrong in the first iteration or in the second one, what were the big mistakes there that maybe other people can learn from? Okay, first mistake, I think, is don't do something like this on your own. I mean, that was never my goal in the first place. But that wasn't really, I think, a big mistake. It was just very hard to find people at that time. Now it's a bit easier for me as a prof with my own group and with a bit more, you know, years under the belt. But I think for such a project, don't do this as a one-person team. Strive for a group project. The big design flaw in MLr2 was really this wrapper principle, like having wrappers instead of pipelines. That was super ugly. That was bad. And the third mistake was having everything in one large package. I'm also not sure whether I would really call that a mistake that I did intentionally. That I had actually MLr2 also split up into various smaller packages. I was just afraid of the trouble that would create if I submit all of that to Khan. So I guess my mistake there was not being brave enough. Another design flaw is don't try to do everything yourself, even if you are sometimes only 90% like satisfied with stuff. So like having like defaults that the community uses, referring to them, and having like other people do the work for you, and then maybe providing them with intelligent feedback. That's often the much better choice than saying, hey, I like this like a bit, but couldn't be a bit better. So no, I just do everything myself, because at the end, you'll just be overwhelmed by everything. So we really try to heavily figure out, can we kind of cut out certain elements of the thing, and because they are provided by other parties in the communities. I think that's often, sometimes it's actually psychologically a difficult thing, and to do that, and I think that's also very important. And I think if you follow these things, I guess you avoid a lot of the stuff that went wrong in prior versions. I hope we got it at least partially better this time around.
I think we all hope. Just before we end, let's ask the very last question. What about the support for Markov chains in MLr?
None there yet, and I'm not sure whether we would do that. I guess if that would happen, we would have to talk to persons specifically interested in that, and they would have to convince us why that is super interesting. At the moment, it's not planned. But so we are very open for discussion, and we love talking to other people from the community. So maybe convince us that it's a good idea. At the moment, I'm not seeing it.
So to our spectators interested in Markov chains, visit MLr Mattermost and ask about this. Bernd, would you kindly close the screen sharing so we can show all four of us for the very end of the presentation? So again, thank you very much for being here. Thank you, Bernd. Thank you, Martin. Thank you, Florian. We are extremely happy that we had a chance to host you. We are extremely happy that our community had the chance to see a bit what is happening in the MLr ecosystem and how quickly it is growing. And I hope that with each of such webinars, the number of MLr users will grow. Thank you very much for being here, and have a good night.
And before you are terminating the stream, thank you for A, having us here, and also B, maybe more importantly, organizing like this webinar series. Like, we also appreciate a lot this effort, and I think it's a very, very cool thing for the community.
The gratitude belongs to Marcin Kosiński, the founder of the whyr Foundation. He is really the spiritus movens because all these webinars. I'm just, like a rando behind the screen today. Thank you very much and good night.
Bye-bye.
Thanks. Bye.
Thank you.